Hello everyone and welcome back to the channel. In this video, I will show you how a bring your own vulnerable driver attack works in practice. We will look at it from an attacker's perspective. We will discuss how a legitimate driver is abused. We will then move on to discuss and analyze the code and the driver itself. If you're interested in understanding how Windows exploitation, EDR evasion, and modern Windows attack chains work, this is a real world look at a bring your own vulnerable driver from start to finish. With that, let's get started. So here I'm in my virtual machine. I have this driver loader folder inside WSL and I have this folder open in Visual Studio Code. This is the high level to do of what we will discuss in this video, starting with the introduction, what bring your own vulnerable driver is and why it matters, technical background, the target driver analysis, some attack chain demos, and the code walkthrough. So let's start off. What bring your own vulnerable driver is? Bring your own vulnerable driver attack is where an attacker identifies a vulnerability in a kernel driver. Then they embed that driver in their own user process or malware and bring it along with them on an attack. So the executable, the DLL, or whatever their attack payload is, it will have the vulnerable kernel driver embedded inside it, and they will try to install that driver. Once the driver is installed, they will exploit the vulnerability using their user process to gain kernel access. Now, kernel access is a broad term. Kernel access could be gaining access to the kernel memory. It could be doing something in the kernel which they want. For example, killing an anti-malware process, an AV process, an EDR process, etc., etc. All right. So, how does this technically work? A Windows driver is installed via the user process. Windows drivers communicate with user processes using IOCTLs. So, input output communication framework, which is used for communication between user processes and kernel drivers. Now, the when the communication starts taking place, the user process can specify a certain IOCTL command to the driver, and the driver can take the relevant action, for example, kill a protected process. All right. So let's look at a specific driver. I have this ntfs.bin file, which was actually an Avast driver, which was found to be vulnerable and it was part of an attack. So let's look at that in IDA Pro. So let me open up IDA Pro, explorer.exe. And IDA Pro here. I think it should load easily now. No. Okay. All right. So in this specific case, we are looking for some leverage or some kind of vulnerability inside the driver which will help us kill an EDR process. So let's look for terminate. Here we see that there is an API called ZW terminate process which is used by this driver. Let's look at this. Press X over here and it will show the place where the driver is using this API. So press OK over here and we are inside a function. Press F5 here to go to the pseudocode of this function. Now, this is exactly the vulnerable function. How do I know that? Because I can see that it is opening a process over here. All right. And then it is killing the process over here. Now, the issue here is that, let me go back to the pseudocode. The issue here is that there is no check. So when a user process sends an IOCTL message, there should be some sort of check that whether that user process has the required token, it has the required privileges, or if the process is not a protected process, where the process that we are trying to kill, there is no such check over here. Now, if we go back and see firstly, let me rename this function MW kill underscore process. Okay. Now let me do X to get xrefs and find where this function is called from. And we have this function called here, which looks like a case statement. If I convert this to an hexadecimal, we can see that this is an IOCTL code 9988C094. And if we go and look at this function specifically, this is basically a function which is given IOCTL, and based on that IOCTL, it is taking some actions. We can see it here, here, and if we keep on going down, we'll see other functions as well. Okay. So we can rename this function as well, MW IOCTL. Not the best of names, but that's fine. Okay. And so we did not see any kind of checks taking place over here, and we did not see any kind of checks taking place over here. So this is the vulnerability, that a user process can send a message with a specific IOCTL to this driver, and the driver can kill the process that the user process wants to. All right. Now let's close this and let's look at our attack framework. In fact, let me save this and close it. Okay. Now let's go back to VS Code. Driver that was used in the attack, we have analyzed the code, and now we can look at the main.c file. In the main.c file, we have to firstly fix a few things, or in this whole code, we have to fix a few things. The first thing is that we have to embed the driver in this, and for that, I have written a small Python code. It will create or generate an encoded payload.h. It will basically encode the ntfs.bin file in that using a XOR key of 0xbb. So let's open the terminal and let's run this. Let's see if I have that in my history somewhere. All right, that's fine. We can see that encoded payload was generated. The payload is here. The XOR key is here. Payload size is also there. If we go to our main.c, we can see that it initially checks whether this is an admin process or not, or this function or this code is running as an admin or not. This is because it has to install a service, and it has to start a service as well. It requires admin and privileges for that. Now, the question here is, if we are an admin, why do we need the driver to kill a process? Because the action that we need to take is very specific. We need to bypass security tools. The malware or the threat actor is using this mainly to bypass security tools or other tools which are running in protected processes. Okay. So it checks whether it is running as admin. It is running as admin, and it calls the install and start driver. We go here, go to the definition, and we can see that it is setting an output path, a service name, and it is starting to do its business where it is decoding the payload. From here, it will dump the payload to this path, the output path, and from here it is going to start the process. Now there are a lot of things that we need to do. For example, open SCM manager, open service, and then we need to start the service, etc., etc. The code which is used to exploit the vulnerability is quite minimal. There is a lot of error checking going on in this code, which is why this code is a bit longer. Okay. So here the driver installation is complete. After the driver installation is complete, we print the task list for the user. And from there, we open up the driver so that we can communicate with that driver using create file w. This will open up a session, and from here we are sending it an IOCTL command using the device IO controller and the process ID that we ask the user to input. Now let's see this in action. Let me compile this code. So driver loader.exe. All right, that's fine. And let's see, and dot slash. Okay. Waiting for driver to initialize, and we have given the processes to the user. Let's see, system informer, yes. Let's look at the details for all processes. Yes, put this here and put this here. Let's sort by username. Let's sort by username like this so we can see all the NT authority things, and we can kill this process 5584 5584, and we saw that the process was terminated. That was a quick analysis of how the bring your own vulnerable driver works. That's it for this video. Thank you very much for your time.